On to part 2 of our revisitation of space-time diagrams. And the subject here is quote-unquote cool plots. Quote-unquote don't be a square. I don't know how it translates into other languages or something, but the idea is if you want to be cool, you want to be with it, then you don't want to be a square. What does that have to do with what we're doing here? Well, as you'll see, maybe just you can see from the diagrams already, we're doing some sort of strange type of plotting here. So let's see what we've got. Non-square plotting, to bring it back to don't be a square. If you don't like that reference, you can ignore it. It's not important for our purposes here. So here's our normal, we're just doing XY plots to start off with here. Okay, so we've got 2 dimensions, x-axis, y-axis. You could imagine maybe we have a field or a whiteboard, and we want to plot points in the field. Or a surveyor, maybe we want to mark locations of various things within a field, or just mark locations of various things on a flat surface. And clearly we have our scale on here. So this is x1, y1, this set of axes. This point here is x1 equals 2, so 2 over for x1, y1 equals 3. The point 2, 3 there. Nothing surprising about that. But you could say, why do we have to have our axes at right angles? This way we've always done it, and maybe it makes sense in some ways, but if you think about it, there's clearly no reason why we couldn't do it this way. We couldn't have the x-axis horizontal again, and the y-axis at some angle. So let's just consider that a minute. Note that the plot then, if I'm going to plot the point x2, so I've got x2 and y2 versus x1 and y1 over here, so a separate set of axes now. x2 equals 2, y2 equals 3. So note how we plot that. So we go again over x2, but then we go up parallel to the y-axis, the y2 axis. So that's 1, 2, 3 there. So that's our point. x2 equals 2, y2 equals 3. And we're going to come back and do a comparison of these two situations in just a second. But we could go one step further and say, hey, let's get really wild here. Why not put the x-axis at an angle as well? And so that's what we've done in our third example here, where we've tilted up the x-axis at some angle. We've got the y-axis tilted at some angle as well. And so in this case, with the x3 and y3 axes, the point x3 equals 2, y3 equals 3. Again, we go 2 on the x3 axis, and then parallel to the y-axis up 1, 2, 3. And so that's where the point is on that plot. Now, I hope if you think about it a minute, you can see that if we're plotting a field, surveying a field, or just points on a flat surface like the whiteboard here, any one of these would work as long as we're consistent about it. Again, it'd be a little strange to do it in these second two cases, but we could certainly do it. We could say, let's define the x and y axis like this, and then for any given point on the board here, we could say, okay, that has an x3 value, so maybe over here, you would have a negative x3 value over here, and sort of a negative y value too, y3 value, and so on and so forth. So any given point could be plotted with the x3, y3 coordinates, or the x2, y2 coordinates, or the x1, the normal, quote-unquote, normal x1 and y1 coordinates. Note that I could use any of the three of them, but note that the 2, 3 point in each case is actually a different point on the board. Let's assume that if we superimpose all three of these so they all have the same origin point, so we took this origin here, put that on top here, and took this one and put this on top here. I won't draw it because it gets really messy. It's hard to draw it. But if we superimpose all three of them, especially in this case, you can see clearly the x3 equals 2, y3 equals 3 point would be way up there. So if we moved that over here and superimposed it here, then that point would probably be, just roughly speaking, be someplace up here. Right? Would be different from the x1 equals 2, y1 equals 3 point. And in fact, for this one too, again, we didn't draw it quite to scale, but it clearly would be at least over this direction more, someplace, might be up here someplace or something like that. So the point being is the coordinates of our three systems are different. Okay? So if I do 2, 3 here is a different point for 2, 3 here is a different point for 2, 3 there. Again, assuming I have all three of them superimposed with the origin at the same point. Another way to think about that is If I have, let's do the most obvious example. If I have this point here, okay, and I'm measuring it in those coordinates, and I get, okay, x3 equals 2, y3 equals 3 for that, what would those coordinates be if I transformed them into the x1, y1 coordinates? Because it's a different point, okay? This 2, 3 point here in this coordinate system is a different point than the 2, 3 point in this coordinate system. In fact, as we've drawn it here, just roughly speaking again, by eyeballing it, let's say it's up here. So this is the y3, oops, not y3, x3. x3 equals 2, y3 equals 3 point. If we superimpose the two, that point we're talking about is right there. And we can ask the question, what's the value of that? So let's just get rid of this for the moment here. What is the value of this point in the x1, y1 coordinate system? Well, again, just sort of eyeballing it, we can see, okay, it's something like this, like that, and maybe 1, 2, 3, 4. So maybe it has a value of x1 equals 4, and y1, 1, 2, 3, 4, maybe 5, 4 or 5 or something like that. Okay? I hope that reminds you of something. It should remind you of things like the Galilean transformation and the Lorentz transformation, because in those cases, we're transforming between coordinate systems. We did a lot of examples with the Lorentz transformation with Alice and Bob. Alice having her frame of reference, Bob having his frame of reference, and Bob has a certain coordinate system in his frame of reference, and we using the Lorentz transformation, if he has any given point, space-time point in his frame of reference, we transform it into Alice's frame of reference, her coordinate system in space and time, using the Lorentz transformation. Same exact idea here. We could have this coordinate system here. For whatever reason, maybe Bob chose this crazy-looking coordinate system. Alice chose a more regular, normal system. And they would want to, if they were both surveying the same field, using the two different coordinate systems, they would have to have a transformation between them. So if Bob measured something and say, hey, I got that, that well over there that we're surveying for in our field is at point 2, 3, x equals 2, y equals 3, would not be Alice's coordinates for the well, x equals 2, y equals 3. It'd be something else. Maybe, as we said, maybe 4, 5 there. Okay, so that's why we're introducing this idea, because as we will see in the next video clip or so, is that this type of thing is going to be useful, because what we'd like to do is put both Bob and Alice on one plot using two coordinate systems. So two coordinate systems in one plot. So the idea is something like this. We're going to superimpose it on our regular type plot so we can get an idea of what's going on in this Lorentz transformation back and forth between the two frames of reference. Before we finish this video clip, though, I want to make one other point here, and that is we talked about lines of simultaneity in a previous video clip. Really, lines, we'll say lines of same location first, and lines of simultaneity, or lines of same time. Same time, so that's simultaneity. Okay, remember, lines of same location are lines in our coordinate system that mean everything happens at the same point in time. And remember also on our regular coordinate system, lines of same location are just vertical lines at any given point. Extend it down below too for negative time if we want. So that's the x equals 2 line of the same location. Anything that happens at that location at any given time will be on that vertical line. And then lines of simultaneity, lines of same time, are the horizontal lines on this plot. So they say any event that happens at the same time that is simultaneous with another event, both those events will be on the same horizontal line, the same value. Now, let's see, I was using generic values for y here, so now we're talking about, let's change this now to our t values, because we can certainly do a plot with, instead of xy, surveying like a plot of land. Now we're going to survey space-time, and space-time in one dimension. So we have the x-axis for our dimension, and then time axis for the other dimension. And so this becomes t3 here. Okay, so now we've turned them into space-time diagrams. Same idea applies. Any of these are valid, just different ways of doing it. But just because we measure at 2, 3 in one position here, and actually then let's change all these two. Be consistent here. So this is T2, T3, and we got a T3 here, and so on and so forth. Just because we measure an xt point, a space-time point there with certain coordinates, it's going to have different coordinates in another coordinate system. And really, if you think about it, that's what's going on with the Lorentz transformation. Bob measures an xt event, an event at a certain xb and tb location. We transform it into different coordinates in Alice's frame of reference using the Lorentz transformation. So back to the point here, though, lines of same location, lines of same time, or lines of simultaneity. Vertical and horizontal here, note that they're parallel to the respective axes. And the same thing when we get these skewed plots, as it were, these non-square plots, the lines of same location here are going to be like this. They're going to be parallel to the t-axis because the t-axis is the line of same location for x equals 0. Oops, that's not a t1 there. Sorry about that. It should be a t2. But anyway, same lines of same, oops, curved line there. So lines of same location on this plot are parallel to the time axis. Lines of same time, because the x-axis is horizontal here, are still going to be the horizontal lines there. So that is what our lines of same location, same time, lines of simultaneity would look like. Again, the horizontal lines being lines of simultaneity. On our third plot here, though, both lines are skewed. And again, they're always, the lines of same location, same time, are always parallel to the appropriate axis. So that in this case, we've got lines like this, roughly not crooked, of course, but nice straight lines as much as possible, like that. Those are the lines of what? Well, those are the lines of constant x values, so constant location, same location. Those are the lines parallel to the t-axis. Lines of simultaneity are the lines parallel to the or the x-axis. So they go like this. Okay? So it's important to sort of get that concept down because we're going to be using that in the next video clip or two or three. It'll come up very shortly here. Okay, so again, cool plots, don't be a square. So non-square plots, perfectly legitimate. We usually don't use those, but we will find that a plot actually like this, we're going to superimpose it on a plot like this because we'll find that that's what the Lorentz transformation is telling us to do when we're going between one frame of reference to another frame of reference. So that's coming up.